Definitely.
Okay, so we have a speaker, we have a title, and we have a co-author. The world is perfect. Please.
Okay, so first of all, thank you, Mel, for the invitation and the opportunity to speak here today. So let me start by saying that, as I just mentioned, everything I will be saying here today is part of an ongoing collaboration with Isabella Laba, which is here in the audience. Now, I want somehow to align expectations. So I think most of the talk today will be devoted actually to just tell you a little bit about the problem. So I'm guessing most of you know what tilings of the integers are, but I'm going to spend most of my time explaining what the Coven-Meyerowitz tiling conditions are and everything around it. That means, more specifically, the connection between cyclotomic polynomials and structure of tiling sets. Okay, so let's start with an introduction, a short introduction about tilings of the integers. So we say that a set A, a finite set A of integers tiles the integers by translations if a disjoint union of translated copies of A cover the entire set of integers, or alternatively, you can think about a translation set T, and you want for every integer X to be uniquely represented as a sum of an element from A and an element from T. Okay, so let's take a look at some basic examples. So let's start with the set 0, 2. So with the set 0, 2, it's clear that you can take a copy of that set, place it at 1, 3, and therefore you've covered the entire interval from 0 to 3, and then you can repeat that pattern periodically. The same kind of idea you can do with the set 0, 4, 8. Again, you can place copies of it at locations 0, 1, 2, and 3, and cover the entire interval from 0 to 11, and repeat periodically. So it is very tempting to think that the tiling period for this set is actually 12, but if you pay attention closely, you'll see that this set is actually uniformly distributed mod 3, and therefore the tiling period for that set is actually 3, and rather than 12, or actually the minimal tiling period. Okay, so let's take a look at the third example. So with the set 0, 1, 3, it is also kind of clear that there is no translated copies of that set that can bridge the gap between 1 and 3, and therefore this set does not tile the integers. And what we'll be talking about today is the conditions under which one can determine whether a given set tiles or not. Okay, so let's talk about periodicity. I just mentioned that. So a classical pigeonhole principle argument by Newman shows that if a set A tiles the integers, in particular, it tiles it periodically with a period M, which is bounded by 2 to the power of the diameter of the set A. Now, this means in principle that you can give a set to a computer and ask him to check whether a set tiles or not. However, you can see that even a set with very few elements might have a huge diameter, and therefore this might take a very, very long time. So we're looking for a better way to determine whether a set tiles or not. I should say that this bound on the tiling period has been significantly improved, but I will not talk about that at all today. Okay, so there are better bounds on the tiling period. Now, in 1998, Coven-Meyerowitz proved, relying on a beautiful theorem of Tiedemann, that if a set A tiles the integers, it also tiles the cyclic group Zm, where M, the order of the group, has the same prime factors as the cardinality of A. Actually, the theorem of Tiedemann they're relying on is a theorem that says that the tiling property is preserved under dilations by factors which are co-prime to the cardinality of A. Okay, so after we have that theorem, we actually reduce the tiling of the integers problem to the problem of tiling of cyclic groups Zm with addition mod m, and instead of thinking about a tiling set, about a tile and a translation set, now we have a tiling pair A and B, which tiles Zm, and we can choose which one would be the tile and which one would be the translation set. Yes, so another important concept is the way we're going to measure distances between elements in both the sets A and B of a tiling pair in Zm. So the way we're going to do it, this is taking the GCD with the tiling period M. And we're going to define the set of all pairwise distances in the set A, and that's going to be the set div A. And the reason we're doing that is because we want to use this theorem of Sand's from 1979, which determines equivalent conditions for tiling, which says that both the sets A and B have to have the right cardinalities, and we want the divisor sets or the distance sets of A and B to have only the trivial intersection. Okay, sometimes I'm going to refer to that property as divisor exclusion. So divisor exclusion between A and B means that the intersection between the different sets is only the trivial one. Okay, so let's see, before we see some examples. So I think probably all of you know the Chinese remainder theorem. So through this theorem, we can identify the group Zm with a direct sum of the groups, each of which corresponded to a maximal prime power, for each of the prime factors of the tiling period M. So now, using this identification, instead of tiling the group Zm, we're actually going to try and tile the k-dimensional box whose dimensions correspond to the prime powers to the distinct prime factors of the tiling period. Now, it is at this point, it is also tempting to be thinking about this problem as trying to tile the lattice Z to the power capital K, but we are actually using the fact that the dimensions of the box correspond to different prime powers or to powers of different primes. And so these are actually different problems. Okay. So I'm going to show you quite a lot of pictures. So just to make sure we're all on the same page, let's start with a very basic example. So I'm going to use my annotation. Let's see. Okay, so in front of you, you're looking at the group Zm, where M is pi squared, pj squared. This means that we're going to have two dimensions, that's two distinct prime factors. And in each direction, we're going to have two scales, the top scale, which is either M over pi or M over pj, and the bottom scales, which is M over pi squared and M over pj squared. Okay, so in this picture, for instance, the distance between, say, point A and point B is M over pj. And the distance between point A and point D is M over pi, which means that the distance between the point B and point D is going to be M over pi pj. Let's take a look at a couple of more examples. So the distances between both A and B to the point C in this picture is going to be M over pj squared. And the distance from A, B, and D to point E is going to be M over pi squared, pj squared, or alternatively, you can just write 1. Okay, is this clear? Okay, so I'm going to use that repeatedly. So if there are any questions or something is not clear, please just stop and ask. Okay, so I'm not sure it's clearly visible in this picture, but what I tried to denote here is the line passing through the point A. This is this bottom line right here. It's supposed to be in a different color. I'm not sure how visible that is, Anyway, that entire line signifies the coset of all elements whose difference with A is divisible by pi squared. And in a similar way, if we're looking at the union of all the lines, so these are all the lines whose pairwise distances is m over pi. So the union of all of these lines is the coset of all the elements of Zm whose difference with x is divisible by pi. This representation turned out to be quite useful for us. This is why I'm spending some time explaining these pictures. Okay, so let's take a look at a couple of three-dimensional pictures. So in three-dimensional setup or 3 prime factor tilings, I'm only going to lay out the top scale grids, because otherwise, if I'm going to include lower scale grids, it's going to be a complete mess. So what you're looking at is the grid such that any two vertices on that grid, sorry, any two neighboring elements on that grid are at distance either m over pi or m over pj or m over pk. So on the left-hand side of the picture, what you're looking at is the maximal length arithmetic progression of step size m over pi. And on the right-hand side, this is the maximal length arithmetic progression of step size m over pi pj. Okay, that's how they're represented in this geometric representation. Okay, so some examples of tilings. Let's start with highly ordered lattice structured tilings. So we have here two examples. In both pictures, we have the points, the elements of A denoted by red dots, the elements of B by the blue dots, and the green dot is the intersection of A and B. Again, we're looking at Zm with m equals pi squared pj squared. And I would like to draw your attention to the fact that, again, these are highly ordered tiling sets. I hope that it's clear that in both examples, the sets that you see in front of you actually tile. If not, then I would be happy to explain. And you should think of these pictures as modular. So the edges are glued right and left and bottom and top. Okay, so now let's complicate things a little bit. Okay, so now I placed the original pictures right at the top, right and left, and below. What I kind of wanted to illustrate what we went through when we started working on this project, because what we've noticed is that if you start with a highly ordered tiling pair and you try to mess up one of the sets, this will come at a cost that the other set would have to have a much more rigid structure. It would have to remain a lot closer to the original highly ordered structure. Okay, and you can also feel this is true because of the divisor exclusion, because if you start with a highly ordered set, you get very few differences in your set. And if you start messing up things, you're adding more differences to your set, and this will come at a cost. Well, since both A and B compete over the same set of differences, if one has many differences, then the other would have to have few. Okay, so this kind of illustrates the idea that messing up one of the sets means that the other one has to remain highly structured. Okay, one last example of three prime factor tiling. Okay, so here I placed A and B on different grids, but just this is just in order to make sure that it is somewhat understandable what's going on, because if I place them on the same grid, it would be a complete mess. So, but you should think of them as being as living in the same group. Okay, and the same kind of principle applies in the sense that if you try to start with these lattice structured tiling pair A and B, and you try to mess up one of the sets, then the other set would have to be highly ordered. Okay, So let's talk about the Coven-Meyerowitz tiling conditions. And for that, we need to introduce polynomials to the picture. Okay, so tilings are translation invariant. So we can translate A and B and assume that they're contained in the non-negative integers. And we can also assume that 0 is the common element of A and B. And now we can define the characteristic polynomials or the mask polynomials of A and B. So how is it defined for A? This would be simply the sum of x to the power A, where A varies, little a varies to the elements of capital A. And now the fact that A and B is a tiling pair now becomes equivalent to the product of these two masked polynomials having the mask. So this product must equal the masked polynomial of the entire group Zm, mod x to the m minus 1. Okay, so this is what we're seeing in front of you. This is an equivalent condition. And after we have that representation of the product of these two polynomials, we can discuss factorizing the right-hand side polynomial. And for this, I want to introduce cyclotomic polynomials. Again, I'm pretty sure all of you are aware or highly familiar with that concept, but just in case. So the S cyclotomic polynomial is the unique monic irreducible polynomial whose roots are the primitive S roots of unity. Or you can define it through this inductive formula you're seeing in front of you. And now having the product of A and B equals the masked polynomial of Zm, this gives us another equivalent condition, which is we're going to require that A and B have the right cardinalities. And for every cyclotomic polynomial that divides which corresponds to a divisor of capital M and which is different than 1, we would like it to, we will require that it divides the product of A and B. But now, since cyclotomic polynomials are irreducible, it means that it must divide at least one of either A or B. Now, before I move on, I want to make a distinction between two kinds of cyclotomic polynomials in connection with tilings. Because with connection with tilings, we're going to make a distinction between prime power cyclotomics and ones which are not prime power cyclotomics. Again, prime power cyclotomics means that S is a prime power, which divides capital M, and all the rest are cyclotomics phi S, where S is a product of two or more distinct prime powers which divide capital M. Okay, the latter is going to be referred to as mixed cyclotomics. So we're going to have prime power cyclotomics and mixed cyclotomics. Now, with respect to this condition that that phi S has to divide at least one of A and B, we have a distinction. For prime power cyclotomics, they're going to have to divide, each of them is going to have to divide exactly one of A and B. And not only that, if it divides A, it will divide it with multiplicity 1. And the same for B, obviously. Now, for mixed cyclotomics, we're going to have a completely different, actually the complete opposite. So a given mixed cyclotomic may divide both A and B at the same time. And if it divides, say, A, it might divide it with a certain multiplicity. And none of that is contradictory to the tiling assumption. These all actually happen or may happen in reality. Okay, so please keep in mind the distinction between prime power cyclotomics and mixed cyclotomics. So now we're in a very good position to state the Coven-Meyerowitz theorem. And this is stated in terms of the set S sub A, which is indeed the set of all prime powers, which corresponds to a divisor, capital M, and such that the corresponding cyclotomic divides the masked polynomial of A. Okay, so what Coven and Meyerowitz did is that they defined two conditions. Condition T1. So condition T1 says that if you evaluate A at 0.1, that gives you the cardinality of A. and this would have to be equal to the evaluation at point 1 of the product of all prime power cyclotomics in the set, which corresponds to elements of the set S sub A. Okay, now this is actually a fairly simple condition to understand. This is just a cardinality condition on a set A. It's not only easy to understand, it's also rather easy to prove. Now, condition T2, let me read it out to you. So what does condition T2 say? You take any collection of powers of distinct primes from the set SA, and what you require is that the mixed cyclotomic, which corresponds to the product of these prime powers, to also divide the polynomial A. Okay. Now this condition is much deeper and much more difficult to prove or to verify. And part of what I'm going to do in the probably until the end of this talk is try to make some sense into this condition. Try to help at least if by the end of this talk everyone will understand more or less what this condition means, I will be happy. So this is more or less what we're going to do until the end of the talk. Okay, so what did Coven and Meyerowitz prove with respect to these two conditions? So they proved that condition T1 and T2 combined are sufficient for tilings. Condition T1 is necessary, and condition T2 is necessary provided that the cardinality of the set A has at most 2 prime factors. So I'm going to elaborate on the first point and the last point. So let me start with the last point, actually. So we were naturally interested in extending this last point to the situation where the cardinality of A has more than 3 or more prime factors. Now, let me say a few words about Coven and Meyerowitz approach and why it simply does not work for more than 2 prime factors. So what did Coven and Meyerowitz used? So they used the fact that when A has at most 2 prime factors and it tiles the integers, it's going to tile also a group Zm where M also has at most 2 prime factors. And then what they did is they used the fact that in this situation, either A or its tiling complement must be contained in a proper coset of Zm. Now, when that happens, you can take the other set, partition it to cosets as well, and then the original set, which is, let's say that A is contained in a coset, the sum of the direct sum of M with either one of the partitions of B is going to tile a proper subgroup of Zn. And then you can repeat that process, and eventually you reach to the point where the T2 property is trivial. You can actually
something did not parse about that last sentence. I'm sorry. Could you go over that one again?
Yes, of course. So again, let me start over. Okay, so if A tiles Zm, what Coven and Meyerowitz used is the fact that either A or B is contained in a proper subgroup of Zm. Okay, let's say that A is the one contained in a proper subgroup of Zm. And then what they did is they partitioned B into matching cosets. And then each of the partitions of B will tile with a tiling complement A, a proper subgroup of Zm. Okay, and this is how you reduce from a tiling of Zm to a tiling of a proper subgroup of Zm, and you keep on going until you reach the point where T2 property holds trivially, and then you just lift up the T2 property to the original sets. That's a fairly standard process in relation to tilings. Now, the main drawback of that approach when you try to work with A that has 3 prime factors or more is the fact that this is simply not true anymore, that one of the tiling pair has to be contained in a proper subgroup or in a proper coset of Zn. This is simply not true, and there are examples of Szabo from the 80s that show that this is not true for 3 prime factor tilings or more. So their approach simply does not apply for 3 prime factor tilings or more, and we had to start over when we just started working on this project. We just had to start with a completely different approach because their approach simply does not work for 3 prime factors. Okay, so I'll go back to the first point in a couple of slides, because I'm actually going to show you how one can reformulate condition T2 in a in an easier understandable way using the Coven-Meyerowitz argument and how they proved that the T2 property implies tiling. Okay, so we'll go back to that in a couple of slides. Before that, what I want to show, or what I want to start to unravel, is the connection between divisibility by a given cyclotomic and the structure of a tile. Okay, so I already mentioned that there is a distinction between prime power cyclotomics and mixed cyclotomics. So let's start with prime power cyclotomics. Okay, so divisibility by a prime power cyclotomic is directly linked to the distribution of the elements of the corresponding set. Now I've written down, so let's take for example, a prime power cyclotomic, phi pi to some power alpha. I've written down the the polynomial itself. And now let's look at 2 extreme examples. Let's start with alpha equals 1. So when alpha equals 1, you can see that having phi pi dividing the masked polynomial of A is equivalent to A being equidistributed mod pi. In a similar way, if you take the other extreme, you take alpha to be the maximal power, so phi pi to the ni, this will be equivalent to A being distributed mod pi to the ni within residue classes mod pi to the ni minus 1. Or if you would like to use the geometric representation, you can just look at the system of planes whose pairwise distance is m over pi. And then you take any else, say that the bottom plane has an element of A that I denoted by A naught, then this equidistribution says that you can find pi minus 1 elements of A distributed across the system of planes. They don't have to be stacked one on top of the other. They just have to be somewhere in this plane. Okay, so now let's continue with the reformulation of T2. And this is actually inspired by the construction of Coven-Meyerowitz when they proved that the T2 condition implies tiling. Okay, so I'm going to start with a set A that tiles. We don't have any distinction on the number of prime factors or their powers of the order of the group M. And I want to draw your attention to the fact that this construction that I'm going to show you does not depend on B. So whatever B is, the construction will not depend on that. It actually only depends on the set A. Okay, so we're going to construct the standard tiling complement of the set A, and I'm going to denote it by B flat, and I'm going to refer to it as B standard. Okay, so the construction goes as follows. You start with the set S sub A, which is again the set of all prime powers such that the corresponding cyclotomic divides the polynomial AX. And then you're going to define SB standard to be the complementary set. So that's all the prime powers which are not in SA. Okay, so after that, I'm going to pick just a fix. I'm going to to take just one prime power. So say pi to the alpha from the set SB standard. And I'm going to match it with a difference rho. Rho is going to be m over pi to the ni minus alpha plus 1. And I'm going to define the arithmetic progression of step size rho and of length pi. this is the maximal length arithmetic progression, which does not present any higher scale differences to that progression. So the pairwise distance between any two elements of that progression is rho. Yes, okay, and the main feature, or sorry, one of the two main features of this progression is that if we factor this progression, if we're looking at this masked polynomial and factor its and factor the masked polynomial into cyclotomic components, what we're going to get is that it factorizes exactly to the product of all cyclotomic polynomials, which correspond to a divisor of capital M, and which have a fixed factor pi to the alpha. And we're going to use that in a minute, because now B standard, sorry, yes, B standard is going to be the product of all of these arithmetic progressions. And one of the main features of that construction is that if we're looking at the cyclotomic polynomials, which correspond to a divisor of capital M and do not divide the masked polynomial of B standard, these are going to be exactly all the T2 polynomials of the set A. This means that the polynomial has all its factors in the set S sub A. And now keep in mind that we are going to assume that A will satisfy condition T2. So if you combine the cyclotomic factors of both A and B standard, we're going to actually get the entire set of cyclotomic divisors, which means that they're going to tile. Okay, so this is
something a little puzzling for me. At this point, we're already dealing with cyclotomics that are not just prime powers, right?
Mm-hmm.
Now, a cyclotomic polynomial in general doesn't just have coefficients 1 or 0. What you're saying is that in all of these cases, I'm guaranteed to get something at the end. I mean, the end result, the product is going to be something which is only 1s or 0s, right? Because B flat has to have only 1s or 0s as coefficients.
Mm-hmm. That's true.
So there's going to be, in the process of taking the product, we'll have polynomials with all sorts of coefficients, but after multiplying through, it all disappears. Yes?
This is absolutely correct. This is part of the magic. And this is also part of the difficulty, because if you had a mysterious way of understanding which combination of cyclotomics will actually give you a set, then you have the key for the entire problem altogether. The problem is, or the issue is, that this is a very difficult problem, or at least to me, I would say this is a very difficult problem. So we have to settle with arithmetic progressions that we know how to factorize. We'll see other polynomials that we know how to factorize later on, but we're fairly limited in how in our understanding of the coefficients of the products of, you give me some family of cyclotomic polynomials, you tell me, please take the product of them and tell me what are the coefficients. I can't tell you right away. It would have to be case by case kind of situations. Yeah, but that's an excellent question and part of the difficulty of the problem. Okay, so now we have the set B standard, and we have, given that A satisfies T2, we have that A and B standard are a tiling pair. Now, before I actually show you the theorem that I wanted to have here, let's have a look at a geometric representation of the standard sets. We've actually looked at these sets before, and the only thing I added now to the picture is the initial information on the cyclotomic factors of both A and B in both cases. So you see, for instance, the grid represented by A on the left picture corresponds to the cyclotomic factors phi pi squared, phi pj squared, and so on and so forth. Okay, so now this is inspired by Coven-Meyerowitz proof of how T2 implies tiling. So now the construction that we just saw says that A satisfies T2 if and only if it tiles with a tiling complement B standard, or if you would like a completely combinatorial formulation of the same condition, you can say that A is the maximal set satisfying that each of its translation intersects intersects the set B standard at exactly one point. Now, if this is too arbitrary, I want to give you one more hands-on example in a very particular situation. Okay, so I just wanted to give you the feeling that for any initial set of conditions on the distribution of the set A, you can get a formulation of the T2 condition, which completely avoids mentioning cyclotomic polynomials, if this is what you wish to do. Okay, so let's take a look at the case where m equals pi pj pk squared, and the cardinality of A is pi pj pk, and let's also assume that A is uniformly distributed mod pi, mod pj, and mod pk. And now I want to remind you that this is equivalent to the product of phi pi, phi pj, and phi pk dividing the masked polynomial of A. Now in this case, B standard is going to be the arithmetic progression pi pj pk times zm, and therefore the T2 condition is going to be equivalent to any translation of A intersecting that grid at exactly one point, or if you would like, A has to be uniformly distributed mod pi pj pk. Okay, so again, for any initial condition on the distribution of A, you will get a matching condition T2 in terms of distribution of this kind. Okay, so now we're almost ready to state the main result. I just want to say that over the past couple of decades, ever since Coven and Meyerowitz published their paper, this problem has found its connection to several other very interesting problems in harmonic analysis, which is my main training, but also in algebra and several other fields. Each of these deserve a separate talk, so I won't go into that too much, or sorry, at all today. Just want to mention that there are applications to this outside of the realm of tiling. Okay, so I'm just going to state one of our main results. This is result with Isabella Laba. We proved last year. And what we showed is that when the tiling period M is pi squared, pj squared, pk squared, then both the sets A and B satisfy condition T2. In fact, the paper that we have published already only proves that for the odd case, and the even case is something that we are writing. We've actually had it for quite a while, but now we're finally finalizing it, and it should be out soon. Now, a couple of remarks about the proof. I'm not going to tell you all of the proof, maybe just 1 or 2 points. And if I have time at the end, I'll give you a layout of the proof itself, what the structure of the proof looks like. And hopefully I will be able to show you the part of the proof in which we have actually classified all the possible tilings with that given period. And what we found out, or what we learned in the process, that the most complicated situation is really the Sabo example, in which none of the tiling sets is contained in a proper coset of Zm. Okay, another point is that we've actually developed quite a few new ideas and approaches to this problem in the process. Many of them apply to a far more general situation than the one in which we've managed to prove T2 in. So we are quite hopeful that we can do more than what we did so far. Okay, so let me share some ideas from the proof. And let's start with, so I want to present two fairly simple concepts. The first is the concept of cuboids. Now, cuboids is not our original idea. It already appeared. I want to give proper attribution, so I'm just going to look at the screen to the right of me. So it already appeared in the work of Rede, De Bruyn, Schoenberg, Mann, and many more in connection to vanishing sums of roots of unity. It also appeared in the work of Malikiossis and many more in connection to Fuglede's conjecture on groups. Actually, what we have contributed to cuboids is the study of multi-scale cuboids, which I'm not going to mention at all today. So let's stick to the fairly basic setup that we have here in front of us. So I'm going to stick to 3 prime factors just to simplify stuff. So m is pi to the ni, pj to the nj, times pk to the nk. And so what is an m cuboid? An m cuboid is a 3-dimensional box such that the vertices, the distance between each neighboring vertices of that box is either m over pi or m over pj or m over pk. And we're going to equip that 3-dimensional box with the vertices of that box with plus minus 1 alternating weights. Now, the connection between these m cuboids and cyclotomic divisibilities through the following theorem. So a set A will be, the mask polynomial of a set A will be divisible by phi m if and only if you take any of these cuboids, any such box, you restrict the elements of A to that box, if there are any, and you sum them up according to the weights. And what you want is that the weights will sum up to 0. Okay, so just waving my hands explaining why this makes sense, just notice that I want to draw your attention to the masked polynomial of this m cuboid, delta. So if you take a quick look at that polynomial, you'll see that it factorizes. So the cyclotomic factors of that polynomial actually include all the cyclotomic factors which correspond to a divisor of capital M, but phi m itself. So combined with A, delta and A share all the cyclotomic factors which correspond to a divisor of M, and that kind of gives you the result you see at the bottom. Okay, you still have to show something, but this is essentially the reason why this is true. Okay, so another concept I want to mention is the concept of fibers. Again, I'm only going to mention.
Could you back up just a second? A weighted set. So what's a weighted set? You can obviously, if you don't belong, then your weight is 0, right?
Mm-hmm.
And you can belong with weight 1 or weight minus 1. That's what's happening.
Yes, exactly.
And you don't have any other possible weights, I hope.
Well, actually, that also applies to multi-sets with weights which are negative or positive. This doesn't have to do with sets, actually. That applies also to multi-sets.
Okay. So you're thinking of, given any polynomial with integer coefficients, whatever they are, you can define a weighted set where the weight is the coefficient of the relevant.
Right, and you see the formulation at the bottom. It doesn't restrict any to right. So okay. Yes, right. So sorry. The formulation at the bottom does say that it's a set, but it also applies in a much more general situation where you have a multi-set as well.
Okay.
Thanks. Okay, so what is an M fiber? An M fiber in a fixed direction, say in the pi direction, is simply a set of the form you see in front of you. Actually, this is simply a maximal length arithmetic progression of step size m over pi. Okay, so this is an M fiber in the pi direction is a maximal length arithmetic progression of step size m over pi. So in the picture in front of you, you're seeing 3 M fibers in 3 different directions. So say the green is in the pj direction, the blue is in the pi direction and the red is in the pk direction. Okay, and we're also going to say that a set is m-fibered in some direction if it's composed of, or if it can be decomposed to it as a disjoint union of m-fibered in that fixed direction. Now I want to cover the other part, which is the connection between mixed cyclotomics and the structure of a set. So this is going to be the next part of the talk, in which I'm going to try and convince you that the cyclotomic phi m somehow determines the structure of the set on what we refer to as M grids. So what is an M grid? An M grid is the arithmetic progression the M grid lambda xm is the set of is the arithmetic progression of step size m over the product of all the distinct prime factors of capital M. Or if I also drew a very particular example where M has 2 prime factors, and then that grid is simply the arithmetic progression of step size m over pi pj. Just to give you an idea of what that grid is. And for 3 prime factors or in 3 dimensions or more, you can just imagine what that extends to. Okay, so next I want to prove a lemma which only applies for the 3 prime factor situation. It would actually be interesting to try and extend it to 4 or more prime factors. And the lemma says the following. So suppose that phi m divides A, and one of the top differences, m over pi, is not a difference in A. And we're going to assume in addition that this pi is not 2. And this is going to be crucial for the proof. In this case, what does the lemma say? It says that if you restrict A to any M grid, then the elements of A are going to belong to an M fiber in either one of the other directions. So on each of these grids, you can have either all the elements belong to an M fiber in the PJ direction, or all of them belong to an M fiber in the PK direction. Now, a couple of remarks. First remark is that this is not a lemma about tiling. So that actually applies regardless of tilings. Whenever you work with cyclotomic polynomials, you can use that lemma without the assumption of tiling. And the other remark is that when pi equals 2, then we have counterexamples to this lemma. So this is simply not true. And this is part of the reason, or should actually give you kind of a feeling why we have split the odd case and the even case into two separate papers. Okay, so let's prove this lemma. This is not a complicated thing. It will only take us a couple of minutes. So let's fix some element A, and I want to show that this element must belong to an M fiber in either the PJ direction or the PK direction. And I remind you that we have assumed that M over PI is not a difference in A. Okay, so let's assume that this is not true. So we can find 2 elements which are not in A at distance M over PJ and M over PK respectively from the point A. Also, since PI is not M over PI is not a difference in A, we can also find 2 elements. Here I'm using the fact that PI is at least 3. So we can find 2 elements outside of A, xi and xi prime, at distance M over PI from A and from one another. So if this is too confusing, let me show you a picture that would clarify everything. So we have the point of A in red, which is small a. And then we have xj, which is outside of A, at distance M over Pj. We have the same, you have xk at distance M over Pk. And we have xi and xi prime at distance M over Pi. And now I'm going to zoom in and consider the cuboid, the M cuboid, with vertices at A, xi, xj, and xk. Now, just imagine that you apply plus minus alternating weights to the vertices of that cuboid. And you can see that in order to balance it, since xi, xj, and xk are not elements of A, in order to balance it, you have to have an element of A at the opposing corner across from A. And now I'm going to repeat the process with a cuboid moving the vertex from xi to xi prime. And again, by the exact same consideration, we're going to have an element of A at the opposing corner across from A, but now we have two elements at distance m over pi from one another, and that contradicts our assumption. So this cannot happen. Oh, sorry. So what we just proved is that all the elements of A has to belong to an M fiber in either the Pj or the Pk direction. Now, if on a fixed grid, we have a uniform choice of the direction, we're done. Otherwise, we would have to have a picture like that, two fibers in two perpendicular directions. But in this case, again, we have now two elements. We will have to have two elements at distance m over pi from one another, which is, again, it's not allowed. Okay, so that concludes the proof. Now I want to show you a quick corollary, and I think we'll be finished at that. Now this corollary says that in the plausible, completely plausible situation in which phi m divides both A and B, then at least one of the sets has to be fibered at the top scale in some fixed direction. And for the moreover part, I'm not going to discuss that right now. Okay, so this is actually a proof in 3 lines. So we're going to use the pigeonhole principle. We have 3 top differences, m over pi, m over pj, and m over pk. You can divide them as you wish between A and B. Let's say that 2 of them do not belong to the different set of A. Then at least one of pj or pk has to be at least 3. And then you can apply the structure lemma, and you get that A has to be M fibered in the pi direction. And that completes the proof altogether. Now, maybe one more word and I'll be done with that. I just want to show you one last picture. In this picture, what you're seeing is actually all the possible skeletons of a tile on a fixed grid, given that given that the corresponding tile is divisible by phi capital M, when M is pi squared, pj squared, pk squared. We actually have a 4th structure that we have identified, but it is a bit more complicated to share here. So this is actually a part of the classification of all the tiles. Okay, I think this is more than enough. Thank you very much.
Thank you. Thank you. Are there questions for our speaker? So could you just say for a minute, what are some of the connections to harmonic analysis that it's connected with your talk?
Yes. Oh, so first of all, there is the Fuglede's spectral set conjecture. Should I state what it says? Are you familiar with that one?
I am not.
Okay, so it's a very famous conjecture from the 70s of Fuglede, which says that a subset of Rn will tile Rn by translations if and only if the L2 space over that set admits an exponential orthonormal basis. Okay, so it has been almost completely solved. Completely solved in dimension 3 and more. I think in dimension 2 there is still something open, and in dimension 1 it's completely open. In the most general case, it is not known, and there is a result of Isabella Laba from 2021 now years ago, which says that the T2 condition implies spectrality. So once you prove the T2 condition, you automatically solve Fuglede's conjecture for that setup. Okay, so any extension of and now actually T2 is a stronger conjecture than Fuglede. It implies Fuglede. The other direction is not known, by the way. This is just one example. There is also an open problem which is called the Favard length. Isabella has worked on this quite a lot, and you can find a really beautiful summary of that topic online. If you just Google Favard length and Isabella's name, you will find a beautiful summary of that problem.
Right. So, Itay, can you close your screen share?
Of course. Pause here. Okay, got it.
Oh, good.
Yes.
Okay. Just get to see everybody else better.
Yeah.
Any other questions or comments for our speaker? Well, so these are nice questions, but they're hard. So next week we have a talk, we have a speaker, we have everything but a title and a subject. So he's a speaker from Philadelphia, but his university has been, I guess he's been teaching on Zoom, so he's in Germany. So I have to track him down. Darius Grinberg.
So Car, can you please pronounce this the name? I'm going to say that name quite a lot probably in the future. So it would be nice to have this properly. Can you?
Okay. Yeah,
Grinberg's name?
Fuller, the namesake of the conjecture.
Fuller. Okay.
Fuller. So don't pronounce the G, then you got it. And the D is soft, like.
I think I probably heard that name for 15 different speakers, and none of them has pronounced it this way. So I'm really happy to be corrected.
Okay.
Thank you.
All right, excellent.
Okay. See you guys next week.
Comments or questions? So let's see, let me just stop the recording because